the inner loop, stone, sing split, stone, sing split, stone, sing split, stone, splitting, split, stone, sing splitting stone, the inner loop, splitting stone. Hi everyone, Martin here, welcome to the inner loop. There was only ever going to be 2, possibly 3 parts to this project. But following the upload of yesterday's video, part 3, which was talking about the split and join algorithms, I got this comment here from hairybiker98, and it says, "Hey, thanks for this video, it's useful to understand the coding behind the poems. What was your code looking for in order to split the words? In speech recordings that I've used, there's often no gap or silence between the words, as people's words flow together into one long noise signature." I did do some stuff in order to make this work, and I thought the best way to answer this question is actually to show you the code in operation. So last night I've added some actual graphs into the code so you can watch it working. So let me take you through that now quickly, and then I can tell you about some of the things that I did in the code to help me with words flowing together, and how did I find the gaps between them. So let's look at that now. So hairybiker98, thank you so much for your question. It's triggered yet another whole video. Here's my code. The split code is actually called SAMP because I stole it originally from a sampler that I wrote, but it's called SAMP, so split's called SAMP. Takes a couple of arguments on the command line, and here you'll see how I've managed to help my algorithm along. It says SAMP, and then it says stones 1, so we're going to use the stones 1 video that I made. Then there's a number which is the aggressiveness of the low pass filter. This is what is actually creating the envelope from the audio. And then there's another number at the end which is 60, which says, when you split this up, please can you find 60 words for me. So to answer already the first question from hairybiker, I've helped the algorithm by telling it how many words to look for. I think without that kind of help, the algorithm becomes a lot tougher and a lot trickier. So that was my first little, well, almost cheat really. So let's run this and see what happens. So the first thing you see is this is the waveform of my poem, Stones. Here's some facts about it. It's it tells you the size of the poem, the waveform, number of channels, the sample rate, and how long it runs for, so 50 seconds. It also works out the maximum minimum amplitude. The next thing I did here is to rectify the signal, so anything that's negative becomes positive. I figured that would help me because it flips the signal on top of itself and helps with building the envelope. Basically, because the wave is going to be both positive and negative, it kind of beefs it up. Then the next thing it does, in blue here, is generates the envelope. So what you see here is now there's no wiggly bits under here. This has now calculated the envelope of my poem. And the final thing now, and you can watch it go, you're going to see a lot of numbers going up the screen here, but you can see it's going to now very slowly bring the threshold down. And as it brings the threshold down, you'll see that it starts to detect the peaks and troughs in the poem. Let's run it and you can see it. You can see it counting the words here. It's running down, running down. Okay, so what it's done is it's found 60 words, and at that point it's stopped. The yellow here is the start of the word, and the purple here is the end of the word. I'm going to run this again, but I'm going to run it a bit more zoomed in on the beginning. Same thing again. Now, what you'll see here, this is the first tenth of the waveform. So this is I threw a stone into. What you see here is if you look at the first part here, this purple has actually detected the end, actually much lower than the threshold that we were expecting. And again here the purple has actually detected the end of this, even though the wave is actually now much lower than we're expecting. So the threshold I actually changed to depend slightly upon the duration. So this is another cheat that I've used. If you watch here, you see here where it's detected the end, the threshold that it needs is getting lower and lower. So what I've said in the algorithm is, don't immediately find the end of the word, but as time goes on, become more and more sympathetic towards the fact that the threshold might not need to drop so low. So what this means is that there's a certain point where the algorithm will just cut off and say, oh, that'll do, that's a word. So here, this is actually being allowed to be a word at this point. Right, I'll show you the code for that so you can see what it's actually doing. So essentially the wave has to pass above a certain threshold to be the beginning, and it has to pass, once it's passed above, it's then looking for the wave to drop below to find the end. But here you can see that it should have ended there, but it didn't, because I've actually not allowed it to cut out so quickly. The algorithm prevents that from happening, and let's have a look at that. So here we go. Here's the code. I don't want to bore you with too much C code, but here we're saying if the word's 0, there's no words yet. If the envelope is greater than the threshold, then word is 1. We found a word, and we along is 0, so we haven't moved along yet. And then we note in a little here, we note down the time at which we saw it start. So now we've kind of turned a switch on. We've said we found a word. We've gone above the envelope has gone above a certain threshold, so the word has been found. Now we've found a word, we're going to use the else clause. So as we go along now, if the envelope drops below the threshold divided by 4, so what I've done here is I've said, actually, you've got to go below. You've got to go below the threshold, but 4 times lower. So initially, you've got to work quite hard. You've got to go to 0 before I'm going to be interested in you. But I've added on along here, so I'm also saying that as time goes along, the threshold that you need to drop below becomes less and less. So this will stop the algorithm from getting stuck. It always will reach a point where it will cut off and the word will be enough. There's one final part to this, which I also wanted to discuss. What this does, this bit of code here, is the waveform between each word. We saw the threshold. So my algorithm, the one that I wanted to use, the one that whatever it did was going to be the way that I was going to do this. This was the part of the art. This is the algorithm I was going to use. Whatever it came up with was what I was going to use. As the threshold goes down, it never goes down to 0. So the words are never going to... So when the words are split up, there's always going to be a gap between the words, which is going to be wasted. Because where one ends, it might go down some more, and then come up, and then hit the threshold and go again. Because of that, that bit of time in the middle will be wasted. So what I've said, again, this is a bit of a cheat, because I can do this after the event. If I was processing sound as it came through, I wouldn't be able to do this. I can basically split that bit of lost time between the two waveforms and add it on. So I say, yeah, the threshold found the word there, but there was a bit more time there and there before that make up the whole word. So if the threshold's cut off the beginning of the word, it doesn't matter, because the gap between the words I'm reclaiming. So again, a bit of a cheat there. But that's another way that I've managed to tweak the algorithm. So that's that. Let's see what this actually created. So what did this create? This actually created the commands to use with ffmpeg. So anyone who's got a fairly rudimentary knowledge of writing code in Python or any other thing, you can do this because the hard work has actually been done by ffmpeg. All I've done here with my split algorithm is to take the WAV file, which is just a reasonably easy to open file, processed it, and then created this output, which is the ffmpeg command. Says what's the input file, where do I start, how long do I run for, and what do I call the output. So ffmpeg is what's doing the chopping up. So let's run, say, the first command out of here. And now we have a file. Let's play it. Okay, so as we expect, it didn't chop it up perfectly. We've got but then this is part of the fun of the process. I did create another file. This other file, the dat file, tells you what the clip number is. Tells you it splits each word into two pieces, two parts, the first half and the second half, and it's measuring the amplitude, the total amplitude of the first and second half. And the reason I did that is I was thinking for poetry that some words rise and then fall, or some words are flat, or some words go down and up. I was going to use this data as another way of trying to choose how to join words together. You know, is it a rising amplitude or a falling amplitude? But I didn't in the end use that, so that's just some data there, and maybe if I wanted to go on with this project, this would be the next area that I'd be looking at to really work the rise and fall words together. And as you'll see at the beginning of this video, I also had fun splitting up the inner loop. Let's have a look at that. Here we go. Here's another example. This is me saying the inner loop, splitting stone. And again, it actually kept the inner loop as one word at the beginning there, the inner loop, and then splitting stone. So just to summarize the algorithm. First thing was I knew how many words I was looking for. Second thing was the algorithm was based on bringing the threshold down, bringing the threshold of the envelope down, and counting how many words that produced. And so I just kept bringing the threshold down and down and down and down until I produced the number of words that I was looking for. Number 3, I used a bit of a cheat for the end of the word to make sure that as time went on, the threshold that it had to go below became higher and higher. And also the threshold that it had to go below was a lot lower to start with. So it wouldn't cut off words quickly, but it wouldn't let them go on too long either. So again, I guess if you were trying to process sound on the fly, you'd have the same issue. You'd do something similar. The other thing that I did which I think is significant, is for the project I actually asked the contributors to produce for me something that wasn't a drawl. Okay, well, that's kind of explained what I'm after. So if you can do 1 minute, write something, read it out. We have to be aware that my algorithm is looking for spaces between words. So if it, I don't want you to deliberately kind of go, but equally just be mindful that if it's a drawl, it's not gonna be able to find the difference. Gavin gave me notes which are easy, so easy to split up, and also Patrick's poem was very, very clearly. He really enunciated his words beautifully. So to answer, Harry Biker, that answers your questions. That if this was to be used in as a business critical or some kind of important bit of voice processing software, it's not going to work. But for my purposes, for artistic purposes, for the purpose of what I wanted to do with an algorithm, it was really a way of demonstrating an algorithm and seeing what it would do. So thank you all very much for watching. If you've made it to part 4, congratulations, and I'll talk to you next time on the Inner Loop.